Hello, today I'll be presenting our work on domain adaptation under Missingness shift. My name is Helen and I'm a PhD student at Carnegie Mellon University, and this work was done in collaboration with Professors Balakrishnan and Zachary Lipton. So this problem was motivated by our collaboration with a regional healthcare provider, and we were wondering what proportion of individuals 18 or older had received at least one dose of the COVID-19 vaccine. Well, as of October 2021, according to their electronic medical records, only 40.5% of adults were vaccinated. But if we cross-referenced with data from the Centers for Disease Control in the corresponding provider locations, we would see that the actual vaccination rate was between 75.7% to 90.3%. So what caused this discrepancy? Well, our hypothesis was that patients hadn't uploaded their vaccination records. There were a lot of mass vaccination events that were occurring throughout the pandemic. And for example, if a patient got vaccinated at a drive-through clinic or a football stadium, this information might not have propagated back to the regional healthcare provider. So now suppose that the healthcare provider were to adopt a new intake form. Let's say that they added a question, have you received the COVID-19 vaccine? Well, absent any shift in the actual health status of patients, the distribution of observed data would still shift, owing to the sudden change in clerical practices. So now, faced with data from different time periods or locations, each characterized by different missingness patterns, how might practitioners use this data to produce the best possible predictor on a target domain? Let's start off with some definitions. In any environment E with missing data, we do not observe the underlying clean covariates X, but instead observe corrupted covariates X tilde, where X tilde is given by X element-wise multiplied with a mask variable Xi, which is zeros and ones. And note that 1 minus Xi are the missing data indicators, which may or may not be observed. And also note that an important assumption of missing data problems is how Xi takes its value, so it could be drawn completely at random, dependent on other covariates, etc. Next, we define missingness shift. Assume that the distribution of underlying covariates and labels P of xy is the same in both source and target. Well, missingness shift occurs when the missing data mechanism differs between source S and target T. Now that we've defined missingness and missingness shift, let's define domain adaptation under missingness shift. So suppose that missingness shift occurs between source domain S and target domain T. Given labeled source data and unlabeled target data, our goal is to learn an optimal predictor on the corrupted target domain data. In the diagram above, shaded nodes are observed, unshaded are unobserved, and Xi may or may not be observed. And between the source and target domains, Xi, and as a result, X tilde, change. Also note that often, as in our example with vaccinations, missing data indicators are not observed. For example, if a patient has a vaccination record indicated in their electronic health record, we can be pretty sure that they were vaccinated. However, if this vaccination record is missing, that doesn't necessarily mean that they were not vaccinated. So this is particularly tricky if a substantial number of true zeros now become indistinguishable from missing. To make this difficult setting tractable, we define the domain adaptation under missingness shift with underreporting completely at random, or dams with UCAR setting, which we focus on throughout the rest of the work. So assume that Xi, which is unobserved, is parameterized by constant unknown missingness rates, MS and MT. Then Xi in source is drawn as a Bernoulli parameterized by 1 minus MS, and similar for MT. First, we give some intuition on the cost of not adapting to the target domain. We start with a motivating example where the underlying covariate x1 is drawn as standard normal noise, x2 is drawn as AX1 plus noise, and y is BX1 plus CX2 plus noise for constants A, B, and C. Now suppose we observe corrupted versions of covariates x1 and x2. Let's say that in source, the missingness rates are close to 0 for both covariates, and in target, x1 is entirely missing and x2 still has low missingness. Then we can show that the risk of the optimal linear source predictor in the target domain can be arbitrarily worse than the variance of y. That is, failing to adapt can result in performance that's arbitrarily worse than guessing the label mean. Later on, we'll show how adaptation is possible and we can obtain the optimal target predictor in this scenario. While we don't observe missing data indicators, we briefly consider what happens if we do. So we show that if Xi is drawn completely at random depending on completely observed covariates, then missingness shift can be viewed as a form of covariate shift. Thus, there exists some optimal predictor that does not change across domains. But again, this setting is not the focus of our work, but we just note that a potential interesting extension could be to leverage the DAM's structure to estimate importance weights more efficiently. To give intuition on the effect of underreporting completely at random, we observe that applying the mask Xi resembles the mechanism of dropout in neural networks. Using similar proof techniques as in the dropped out paper, we show that UCAR can also be viewed as a form of L2 regularization in linear models. So let's move on to identification. So first, let's define the concept of M-reachability. For data points A and B, we say that B is M-reachable from A if there exists some mask Xi such that B equals A element-wise multiplied with Xi. So if B is M-reachable from A, then the dimensions of A that are 0 must be a subset of the ones that are 0 in B. And any dimensions that are non-zero in both A and B must match in value. We show that it's possible to identify the corrupted distribution from the clean distribution giving missingness rates M. So consider the probability of any covariates xy in the corrupted distribution. X could have come from any clean sets of covariates Z such that X is M reachable from Z. So we sum over all such Z, and we take the probability of those Z's in the clean distribution, and then for each covariate, we multiply by 1 minus M if it's not zeroed out, and by M if it would have been zeroed out. This identifies the corrupted distribution from the clean distribution. And interestingly, given that M is strictly less than 1, we show that P, the clean distribution, is actually identifiable from the corrupted distribution using induction on the number of dimensions that are 0. But note that we require knowledge of the missingness rates, M. Unfortunately, M is not in general identifiable from data. So consider two possible source distributions, A and B, Bernoullis of rates 0.5 and 0.25. If we apply missingness rates 0.5 to A and 0 to B, this would yield identical observed corrupted distributions, Bernoullis with rates 0.25. Thus, the rates themselves are not in general identifiable from data. But fortunately, we can identify a few things. We can take the ratio of the probability of non-zeros in target and source and show that this equals the ratio between non-missingness rates, so 1 minus MT and 1 minus MS. And so 1 minus this ratio gives us a relative missingness rate, RST. And using this relative missingness rate, we can thus identify the labeled target distribution from the labeled source distribution. And note that the form of this equation below is pretty similar to that of identifying the corrupted distribution from the clean one, which will imply a procedure later. But note that we do need that MS is strictly less than 1 so that the denominator is not 0. Now we talk about estimation. So for estimating the relative missingness rates, RST, we can simply compute the proportion of non-zeros in source, QS, and the proportion of non-zeros in target, QT, and then compute this relative missingness rate. Using Hoeffding's inequality, we can show that with probability 1 minus delta, we have a bound on the error of this relative missingness rate, and it's given in terms of both the proportion of non-zeros in the source as well as the number of samples, NT and NS, in target and source. Now we provide a non-parametric adjustment procedure motivated by the similarity between the identification of target from source as well as corrupted from clean. So we can compute this relative missingness rate from data, and then we can check whether it's greater than or equal to 0, strictly greater than or equal to 0. If it's not, then note that this is not a proper adjustment, but we compute the relative missingness rate as a max of the relative missingness rate in 0, where the max is element-wise. We apply the missingness rate to the source data to get data distributed identically to target data if we have a proper adjustment. Otherwise, it's a different distribution. And then we fit a predictor on the further corrupted labeled source data. We also derive a closed form solution for the optimal linear predictor in target. So this is given by this equation, inverse of the covariances of the target times this relative missingness rate, which is element-wise multiplied with the covariances between the covariates and the label. And so we can estimate the second term already using source data. And in the first term, we can estimate it in two ways. We could estimate it directly from unlabeled target data, or given those relative missingness rates, we could actually estimate it from source as well. And so in practice, if we were to have a lot more source data, perhaps one might want to use this computation based on source data. Or if one has a lot more target data, maybe one would want to use the estimation of the covariance directly from target data. So now let's discuss our experimental results. So we draw 10,000 samples from two simple synthetic data generating processes. In the first, we have redundant features where there's some underlying z, and x1 and x2 both equal z, and y equals z plus some noise. And in the second scenario, we have confounded features where we have some underlying x1, x2 is a function of x1, and then plus some noise, and then y is given as a function of x1 and x2 plus some noise. And in both of these scenarios, we apply missingness rates in source where we have the first covariate is very missing, the second covariate is not really missing, and then in the target domain, this is flipped. And we try this for several values of epsilon. And here are the results from those experiments. So we see that when epsilon equals 0.5, we have that source and target missingness match perfectly. And that's why all of the methods perform comparably, because no adaptation is needed. And then as we move towards the edges where source and target missingness differs more greatly, we see that the source predictor in blue performs worse. The oracle and the closed form adjustment are able to adapt and perform similarly in orange and green. And then in red, we have the non-parametric adjustment where because it's not a proper adjustment, because the target missingness is not strictly greater than or equal to the source missingness, it has intermediate performance. We also have some semi-synthetic experiments which use real UCI data along with synthetically generated labels and missingness. So these are the adult bank and thyroid data sets. So among these data sets, when it's a proper adjustment, the non-parametric tends to outperform or perform at least as well as all of the other methods. However, once we include the not proper adjustments, for XGBoost and MLP, we can see that it no longer always performs best, though often it does perform best or comparable. We also have times when the source performs just as well. And then for the linear models, all of our adjustments seem to perform best. And then for synthetic data, we know that for the XGBoost models, we can actually observe, or XGBoost and MLP models, we can actually observe the source predictor outperforming some of the other methods, perhaps because the missingness induces some sort of nonlinear relationship between the covariates and the label. So in conclusion, when indicators are provided and missingness depends on completely observed covariates, domain adaptation under missingness shift can be viewed as a form of covariate shift. However, in several cases where missing data indicators are not provided, we provide identification and estimation results for the dams with underreporting completely at random setting. And our experiments validate our finding when assumptions do hold. For some extensions, we hope to seek some more real-world data well-suited for dams with UCAR, as well as explore some generalizations or relaxations of the dams with UCAR assumptions. So, for example, allowing dependence on covariates or perhaps exploring other noise models. Thank you for your interest in our work, and feel free to reach out if you have any questions.